Hi everyone, my name is Tintin. Today I will present my new publication in the Astrophysical Journal on the shadows of Kerr naked singularities. This was done with my research mentors, Dr. Sikan Chan and Dr. P. Christian. So what do I mean by shadow? I want to start with a more familiar scenario of the black hole shadow. So imagine you have a camera observing on Earth far away, represented by this white screen. You're trying to look straight into a black hole. And because the black hole has an event horizon or a point of no return that nothing, even light, can escape from, you are just staring at nothingness. You're staring at the void inside a black hole. You're literally looking into a black hole. You can imagine if your line of sight is a bit further away from the black hole, then the light rays just get scattered off instead of being trapped. But somewhere between the scattered and the trapped orbits, you have a region where light can orbit multiple times around the black hole. And this region is called the unstable photon orbits, where effectively your line of sight is looking through the emission of the accretion flow around the black holes many times, and this leaves a very bright imprint on your image, which roughly translates to what you see in the famous donut-like black hole image. This is called a black hole shadow, which I will define to be the projection of the unstable photon orbits, and this is encoding a lot of information on the gravity of the black hole. I have to give disclaimer that there are some subtleties in how the shadow translates to what you actually see in the image, because what you see in the image you need to also take into account other properties like the thermal properties of the accretion around a black hole, while the shadow is a purely gravitational effects. So the main motivation of my project is the recent success in direct image of supermassive black holes captured by the Event Horizon Telescope, which is an array of over 10 radio telescopes across the globe which act like one Earth-sized telescope. And as I mentioned earlier, shadows are direct indication of the gravity of black holes. They are long known to be signatures of Kerr or spinning black holes in General Relativity, or GR, our leading theory of gravity, which are projection of unstable photon orbits and provide us with a direct and highly sensitive test of gravity that is independent from the accretion physics. And future space-based EHT might even provide us a higher sensitive test of gravity, which opens up a lot of promising avenues in this line of research regarding black hole gravity. So we have established that shadows are signatures of Kerr black holes in GR, but shadows have also been shown that it can be mimicked by other theoretical objects or gravity theories besides GR, such as naked singularities, which are gravity singularities not hidden behind event horizon. Singularities are region in space-time where basically the math just blows up to infinity because the gravity just becomes infinitely strong. Other objects that can mimic include boson stars, or you can have space-time without an horizon. You can have deviation from the curved space-time. That can also produce you with very similar closed black hole shadow image. And the Event Horizon Telescope have placed some constraints on these alternative models of black holes and gravity theories from the direct black hole images. So this leads to my study on Kerr naked singularities, which are basically super spinning black holes, except that when you spin a black hole up past a certain theoretical limit, which is normalized to be spin A equals 1. So if spin A becomes greater than 1, then the event horizon of the black hole vanishes, leaving behind a naked singularity. And the theoretical motivation includes the cosmic censorship conjecture, which hypothesizes that all naked singularities have to be hidden behind an event horizon, so they cannot be observed in nature. After 50 years of this conjecture, there is still no mathematical proof to this conjecture. So while we don't have any good reason to believe that naked singularity exists, we have no reason to believe that they don't exist either. Another very interesting paper in 2009 predicts that if we ever can observe naked singularities, it can provide us with a test of string theory. Other studies have shown that Kerr naked singularities, or let me call KNS for short, is unstable in GR. So if we are able to detect KNS in nature, it will provide us with a test of deviation from GR. And also, a recent paper showed that the shadow of the M87, one of the two black hole images, is consistent with KNS when the authors try to prescribe some quantum gravity effects. So in my study, I have the Cartesian coordinates. I place the KNS center around the origin of the coordinates, and the naked singularity has the ring singularity configuration with spin A. I have an image plane effectively very far away, which is placed at an inclination with respect to the normal to the naked singularity. So without going through all the complicated mathematical derivation in my paper, I'm going to show the center results of my paper. So here I have the spin inclination phase space, where on the left hand side, as you go from bottom to up, your spin increases. On the horizontal axis, as you go from left to right, you go from phase on 0-degree inclination to edge on or 90-degree inclination. And we have shown that when the KNS spin is low and our inclination is close to phase on, the shadow of the KNS can still be closed without any gap, just like the black hole shadow. As we go to spin A equals 1.18, which is a critical spin parameter that we were able to derive, then for all inclination, the shadow of the KNS starts to open up with a gap. So now we have an open instead of a closed shadow. And interestingly, when the spin continues to increase past 1.18, the shadow vanishes for low inclination and only re-emerge as you go to higher inclination. And as you go to even higher spin, the shadow vanishes for a greater range of inclination. So just to give you some visualization, let's look at a example of when A equals 1.01. So it corresponds to this red line on the spin inclination phase space. So as you go from low inclination to high inclination, you can see that at low inclination you have a closed shadow without any gap. And when you increase inclination, at some point the shadow opens up a gap and becomes open. At 1.18 on the phase space, you see that there's no inclination, that you have a closed shadow, and this is what we're seeing here. For all inclination, the shadow opens up a gap. And for spin greater than 1.38 correspond to this upper dotted line. For low inclination, the shadow vanishes, and the shadow only re-emerge at spin around 14 degree, and it kind of becomes bigger when you go to higher inclination. So to verify the results we showed earlier, which are based on exact analytical derivations, we run some numerical ray tracing around the KNS, which is basically trying to compute approximate solutions to light trajectories around KNS. So we set up an image plane, again, effectively far away from the KNS. With a grid of photons, we try to integrate the light rays backward in time towards the KNS using the differential geometry package FATCH led by my research mentor C.K. Chan, that I also involved in some software development beta testing of FATCH. So by running these numerical ray tracing simulation, for every photons on the light grid, I compute the deflection angle, which is defined as the angle difference between the incoming photons and the outgoing photons with respect to the KNS. So here you can see that for the red color, it denotes higher deflection angle, meaning light is coming back to the observer, us observing the KNS. And the bluer region represents lower deflection angle, denoting that light is moving to the other side instead of going back to us. So it creates some region of transparency. So how do we interpret the KNS shadow from these deflection angle plots? As I mentioned earlier, the shadow is the projection of the unstable photon orbits. So in the KNS case, it corresponds to a region where light oscillates rapidly between going away from us and going back to us. Or from a more colorful standpoint here, it corresponds to a region where the color of the deflection angle oscillates between red and blue. So here I plot the analytical projection of the shadow on the image plane, and you can see it corresponds to the region where the deflection angle color oscillates rapidly between red and blue. So this is how you can read off the shadow from the deflection angle plots. So we ran the numerical ray tracing experiment and produced the deflection angle plots for a wide range of spin inclination, and again produced a spin inclination phase space. So let's compare the numerical results with the analytical plot I showed earlier. So for the low spin, low inclination case, you can see that we have a closed shadow without no gap. This corresponds to region A on our analytical phase space on the right. And in the region where you go to higher inclination and you go past spin 1.18, then you start to see that the shadow of the KNS opens up a gap for all of these numerical deflection angle plots. Then this corresponds to region B, shadow with a gap. And for higher spin and low inclination, you can see that the shadow of the KNS starts to vanish, corresponds to region C in the analytical spin inclination phase space. So the numerical calculations were able to completely replicate my analytical calculations. So some implications of my project include that I was able to show that KNS shadow can be closed like the black hole shadow we observed from the black hole images. This disproves some of the misconceptions in previous literature that KNS shadow cannot be closed. Also, my study provides an observational framework where we can test cosmic censorship from horizon scale, direct black hole imaging technology. And my project provides a framework or springboard to study perturbations of KNS and other naked singularity types, where you can go with all the types of naked singularities and produce the same steps I did in this paper. So in conclusion, KNS shadows can be closed, open, or vanishing depending on its spin and depending on which inclination we're observing from. We show that analytical results are reproduced by the numerical ray tracing simulations, and this has some implications in testing gravitational physics through black hole imaging. Definitely want to thank you, Dr. Chi Kwan Chan, Dr. P. Christian, for mentoring my research projects. Thank you to the Black Hole Pioneer Group at the University of Arizona for funding my research project with the NSF Pioneer Grant. So thank you all of you for listening, and I hope you learned something interesting from my presentation.